Okay, well, so, in fact, this talk is a continuation of the one that I gave in Oslo when I got the which was a number of years ago. But, I've actually gotten interested in two new subjects since then, and so it's exciting for me to repeat part of what I said then and tell you how it leads into what I've been interested in lately. So we'll see if I get through the whole talk. We'll start with the Greeks and we'll end with a problem that's been annoying me for 50 years. That's it shows how old I am. That's so. The question that found on the web is: do animals do mathematics? They seem to know that the shortest distance between 2 points is the longest straight line. I found that very amusing. But the axiom of Euclid is 2 points are connected by a line, so that was an axiom. The statement by Aristotle was the shortest distance between 2 points is along a straight line. The Greeks did not. I need to see where we are. Oh, okay, good. The Greeks did not have a good description of arbitrary curves. And in fact, when preparing this talk, when we get, it seems that in fact, what happened in the revolution in mathematics was not the invention of calculus. It was the discovery of functions where you could describe, because the Greeks understood the problem, and they also had a lot of techniques to prove things, but they had no concept of a function. And so they gave many constructions of shortest distance and had the machinery to prove that these were indeed the shortest among all the piecewise linear paths, which, if you know what a function is, you can change that into a proof for any curve function. Heron can be proved that this context, the shortest distance path between any number of reflecting mirrors is obtained by using the lines through the mirror to the imaginary reflected points. And one of my favorite ones is Dido's problem, which is in Virgil's Aeneid. That was the greatest area that could be enclosed in the hide of a bull. And of course, their solution was you cut the hide in very long thin strips, and you lay the strip in a circle. Actually, in the Aeneid, it's a semicircle because you're along a shoreline, but it's the same idea. And so that's what we usually know as the isoparametric inequality. And Zenodorus gave a rigorous proof that the regular endon in geometry that achieves the largest area for a given perimeter along all the endons. So fast forward a couple thousand years. So one of the next minimization problems was Fermat, which gave the law of reflection and refraction are achieved by paths along which the light ray is minimal. And so if the path is going from here to here, it will take the shortest distance rather than this and this. And I think there's already a question which we maybe don't ask ourselves enough. Deschambault, who was a philosopher to Fermat, the principle you take as the basis of your proof, namely that nature always acts by using the simplest and shortest paths, is merely a moral and not a physical one, and cannot be the cause of any effect in nature. I think it's because actually you use minimization to all sorts of things which it's not even clear exactly why. So one of the more famous occurrences was the Berkristicum problem. The question is, what is the curve along which a particle falls from P to Q under the influence of gravity in the shortest path? And Galileo was already interested in this, and he proved that the circle is faster than a straight line. And Jonathan Bernoulli in 1696 posed this as a challenge problem. Received solutions from a lot of people we've heard of, Jacob Bernoulli, his brother, Leibniz, L'Hopital, Newton. The story is well known is that Newton received the problem that the mail, when he returned from the mint at 4 o'clock in the afternoon in January 1697, and had solved it by 4 o'clock a.m. He submitted anonymously. Bernoulli is quoted as saying, "We recognize the lion by his paw." The solution is a cycloid, which I was able, I'll show you what later on what the technique for solving the problem is, but I didn't know the equation of the cycloid, which dates me. By 1744, both Euler and Moltke had formulated calculus of variations problems, which were intended to describe Newton's laws in certain cases. Roughly stated, Euler proposed minimizing the energy, which is basically integral P to Q, which this is momentum, and this is Q is space, and dQ is velocity times dt. And the function f is an arbitrary function of time, which is fixed in space at the endpoints of the interval, which is, however, in 1762, Lagrange gave the form we still use today. You minimize the action of the integral from a to b of an arbitrary function of the function and its derivative. Formally speaking, L is any function. In mechanics, the L would be the kinetic energy minus the potential energy, which is where we use it. In Euler's notation, k dt is p dq dt. Q. He also derived what we still call the Euler-Lagrange equations, which hold for simple, single, and multiple intervals. In fact, that's really the invent. I still remember the time when I saw the Euler-Lagrange equations derived from the calculus of variations problem, and it was one of the magical moments when you say, "Gosh, you can do that." That's so. They're defined with any number of vector valued functions. Okay, the Euler-Lagranges for the problem that I wrote down, this one, you take the derivative of L in the direction of the F prime, and then you take the time derivative of that, and minus the partial of L in the direction of Fj is equal to 0. But there's a conservation law which makes this a dual solvable problem. It comes from the invariance of the integral under time translation. And it is, in fact, there's a formula for it. And in fact, when I actually worked on the Verkistikov problem, I used this formula 3 times. I mean, I got the equations, but I had to know this step too. We call solutions of the equations critical or stationary, but they're purely formal. They're also not necessarily solvable. At first, mathematicians were just pleased to derive these equations. Over the next few centuries, they became interested in such problems such as boundary conditions on the ends of the interval, existence, uniqueness, and continuation under which the solutions are minimal. This is an interesting story, but we wouldn't get anywhere near today if we did fast forward to the point at which the analysis was developed. So, Hilbert's 23rd problem is a different flavor from most of his others. It basically comes down to the need to establish rigorously the calculus of variations. When I was a graduate student in the 1960s, the two reference books due to Mori, one due to Mori and one due to Ladizenko and Rotsova just came out. They are very general in nature, involving general multiple integrals, and so it's rather than start with a problem you want to solve, they would write down the most general thing and prove what they could prove by that. But it wasn't directed at solving particular problems. I mean, this was so anyway. And here, so and also it's interesting. The references use derivatives up to order k, and but on the other hand, in the actual application to the calculus of variations, almost all of them have one derivative in them, and two derivatives. There's some very few interesting problems, but I've never seen a calculus of variations with three derivatives in it. That's I'm probably wrong there on many, but so much of the analysis was developed in RN, but it was developed sufficiently so that theorems to do state theorems on manifolds. Machinery was developed to construct infinite dimensional Banach manifolds with geometry. Theorems in finite dimensions, Sart's theorems, the gradient flows, and so forth, were the same in infinite dimensions than in finite dimensions. This is rather startling. You can solve an ODE on an infinite dimensional manifold. The same proof, the Picard iteration, works in infinite dimensions. So this looked very promising. This was actually quite exciting. I mean, to find natural integrals on, say, maps between two manifolds, where M and N are, one might mimic the construction of harmonic functions. For where dimension is greater than 1 and N is equal to the real line, you get a harmonic function, and G of D6 if the dimension of M is 1 and N is arbitrary. So the idea of a harmonic map between manifolds extends both those ideas. Harmonic maps between Riemannian manifolds are critical points of this integral, with just the integral of the derivative of function squared, where you have to compute, you need the volume form from the manifold, and then to compute the norm of df, you need the metric on the base and the metric on the target. So one of the encouraging things is that at this point, Ilse and Sampson proved the image manifold had negative curvature, that there exists a unique harmonic map in every homotopy class, except in a rather trivial case where you map to a circle and then you have the rotation in the circle with it in the manifold to give you a whole circle of solutions. But so that's now their proof was via a gradient flow. I'll talk in a minute about why it doesn't. You can't just use it as a variational problem, and but their gradient flow was technically a heat equation. It was a very important step. That proof of the existence of solutions to the heat equation for harmonic maps was mimicked for decades afterwards. So the direct descent method fails, because to do it properly, one must choose the natural Hilbert space, and the natural space space for the problem is functions whose derivative are square integrable, or that's just the standard notation for that. And these functions are not continuous. And so the algebra does not work out right unless you're working in a space in which the functions are continuous. To find suitable integrals to which the theory applies, the natural space would have to be something like the functions whose first derivatives are in LP. You can also go to second derivatives in L2, and so forth, but those problems just don't work out. In other words, when you have more than one derivative in a variational problem, it does get quite complicated. But if you take the functions whose first derivative are in the space LP, where P is bigger than the dimension of N, those functions are continuous, and the algebra always works out in that way. In looking for examples of this sort, one has led to P harmonic maps. These are the critical points of a function, which are, remember the critical points here, the points are functions in this problem, which are the critical points of the integral, the same as the integral for harmonic maps, but raised to the pth power. And actually, my thesis involved just working out all the details of that map. You have to put a metric on the manifold. You have to look at gradient flows. You have to actually use Stark's theorem to prove that. And also, the hardest part of that problem, by the way, was to prove the solutions were actually continuous. You wanted them to be at least continuously differentiable, or they don't have much geometric meaning. And that was the hardest, which I took years to solve that problem. So sometimes when you work on a not so exciting problem, it turns out to be an entry into some very difficult and interesting problems. So the most famous problem of this was the paper I wrote with Jonathan Sachs, where we modify the harmonic map, and we're in dimension 2, so we're looking at harmonic maps from S2 into a manifold, and the harmonic maps would be just the Royal-Lagrange equations for ds squared, and but if you add an alpha here, where alpha is a little bit bigger than 1, as alpha goes to 1, the solutions could converge to a harmonic map. And for reasons, algebraic reasons, that harmonic map is actually a minimal surface. And the critical points, though, the important part of this problem is it really was based on a Morse theory. That is, if there are any topological reasons for a critical point, this proves there is a critical point. So you don't have to have just minimum, which is somehow. And I actually was able to actually prove the Eels-Sampson result by adding a parameter with a ds to a derivative to the pth power on it. And now this satisfies all the formal conditions. And so you just let epsilon go to 0, and because of the negative curvature, you can get the solutions to a curve. So, and actually, the Eels-Sampson proof is via a heat equation, and this is via an approximation theorem. Basically, it comes down to the fact that the intervals are convex. And any way you go about looking for a minima, you're going to find a minima. And actually, Yao and I used this later to solve a very much quoted problem, use this technique. And actually, at this point, I have to mention St. Yao, because we had all this excitement about global analysis, but the payoff wasn't all that great. And but Yao came along and solved a whole bunch of other problems. And they not only but they use all the modern methods of PDE that have just been developed. I mean, and so, I mean, he solved the Calabi-Yau metrics. Meeks and Yao did minimal surfaces. Shane and Yao did relativity. Siu and Yao did algebraic varieties with a certain geometry or projective spaces. That's and an understanding of scaling took place. In physics, these ideas are from physics. There's renormalizable problems, scale invariant problems, and unrenormalizable problems. And the scale invariant problems turn out to be the most interesting. That's harmonic maps in 2 dimensions and Yang-Mills equations in 4 dimensions. Unignorable means that some extra algebraic condition, negative curvature we saw for harmonic maps, is imposed if you want to control the calculus variations. And I should say at this point that the geometry of Yang-Mills was developed, where the natural geometry, when the gauge group was taken into account, leads to dimension 4 as the scale invariant problem. And actually the other common scale invariant problem is the Uhlenbeck problem. So they're not, okay. So I want to give, what would be a natural application of interest? When I was in graduate school, Mostow's proof of rigidity came out. It says that if M and N are hyperbolic manifolds of dimension bigger 2, and if F maps M to N is in a homotopy class of the diffeomorphism, then there is an isomorphism homotopic to F. A natural proof is actually to construct the harmonic map, courtesy of Yields and Sampson, in the homotopy class, and show due to the geometry that it is isometry. There is still no proof by this method. The method is that the proof that it's an isometry at this point follows from the existence of an isometry, which is a special case of a harmonic map, and the uniqueness, which says there is no other harmonic map in the homotopy class. So and of course, I put this in because I have some new tools to use to take that approach, and I can't make them work. So I'm always hoping someone will. Okay, now we get down to what I've been interested in. Several years I gave a similar talk, actually when I got the Abel Prize, when I pointed out that the minimization problems at greatest interest at the time is the minimization used to construct models to identify data. So this is AI. This is not a calculus variation problem, there is no counterpart to the Euler-Lagrange equations for the solutions. The geometry of the problem seems to be missing. Several months ago, Govard Menon gave a talk on exactly this question. What is the geometry? It is a novel development, and I'll give a short outline. The geometry arises in the extra parameters which are not necessary to describe the data. A term coming from the geometry of the parameter space is added to the gradient descent term, which simplifies the model. It is also not surprising that the geometry of the parameter space is recognizable. And I was particularly interested, and when I attack this with problem, then I know that's like this, is Yang-Mills equations on a Riemann surface. There's an influential paper by Tia and Bad on that. And that has the structure of the same structure, and it was recognized that this has the same structure as the parameter space of the deep linear network. Well, the data X we wish to describe is encoded in capital N, small n by n matrices. W of P and G in the general linear group, where X is the product of the W's. The model needs itself to be described using the complex, the model needs to be described using complex geometry. This is the most confusing part of the whole theory is you want a real answer, but you need to go to the geometry because the geometry actually comes from the complexification. And so to understand it, you need to look at the complexification. And the point is there's a moment map to this to for the action of the symmetry group of all elements in the unitary group. In practice, we would use only the real parameters. Okay. So the goal is to minimize the function, which is the function we'd like to minimize, which is dependent only on the x, which is the product of all the w's. And we add to it a parameter, a correction or a parameter space, which is a function of w. And this parameter space, we're going to have gradient flows which are tangent to the space on which x is fixed. And so these interact in special ways. So here you really, I mean, to understand, I didn't understand for a couple weeks what the idea was. The gradient flow of f vanishes on the differential of the regularizing function, and the gradient flow function of w picks out good representatives of the w. So you have this. There, see, if you want to count, you have a parameter space of n by n matrices, but you can now take capital N of those, so you have n minus 1 times n squared extra parameters. And those parameters that we're actually trying to straighten out. Okay. And as I said, the model is the Yang-Mills equations, and the full gauge group preserves only in the Yang-Mills, the full gauge group preserves only the complex structure, which is what you're basically interested in the T-above, is the complex structure of the group, whereas the unitary gauge group preserves the entire geometry of the problem. And you see in this case, when you divide out the function by the unitary gauge group, you get you get an infinite dimensional manifold, but when you divide out by the full gauge group, you get the complex structures. Okay, so in this problem, the gauge group is the order set of capital N minus 1. So we had n times n matrices, and we have n minus 1 matrices, which are going to act on these n matrices. And these matrices, again, in GLNC, which, and the multiplication is multiplication by the individual matrices. In fact, it takes like this. It takes a WP you multiply it on the left by an element in the gauge group, and you multiply it by the inverse. Good read, I have a pen, I can put a minus 1. And you multiply it by the inverse on the other side. And when you multiply them all together, this one cancels with the one below. And so it doesn't end, it ends up not changing the product, because you multiplied it on the left by one thing and the right by another, and they cancel out when you multiply them together. And okay. So the symmetry group script U in G consists of matrices in the unitary. It consists of unitary matrices, not only complex matrices. It's not only leaves X invariant, but it actually leaves the entire geometry. That is, when you write down an equation and you make a gauge transformation by unitary matrices, you get all the geometry stays the same. The distances, I mean, you can't write down it. If you write down something in which isn't true, which isn't gauge invariant, you want to throw that away. That's not a good idea. And that shows you there's some obvious functionals that you should not look at because they're not gauge invariant. So, so the linear space that you're working is a linear symplectic space. The inner product is just the sum of the traces of the W with WP star, sum over P. And there's a symplectic structure. This is a very simple case. You just multiply everything by I, and that picks out the imaginary part of the sum of this. And so now we have a formula which I guess to Govin anyway, when it first appeared, seemed very strange. There are some functions omega that are dual, and these are symmetric functions, and they're dual in the Lie algebra. In this case, remember that the moment maps in the dual of the Lie algebra. It's not in the Lie algebra. So if you get two different formulas for it, it means that you're using two different definitions of the dual, not that you've done something wrong. Anyway, so in this case, we're identifying with symmetric matrices, the dual with symmetric matrices using the symplectic inner product, whereas if you use Lie algebra inner product, you'll get an I in the answer. It'll be skew symmetric. That puzzled me. I mean, I'm emphasizing some things that puzzled me. Why are these coming out symmetric instead of skew symmetric? Instead of skew adjoint? And let's see. Several geometry. So what sort of regularization functions should you use? Well, I mean, the ones that have been used a lot are things like the norm of W squared. That's the sum of the norms of all the input and the matrices in the products. And then also, however, Govin was discovered from reading the papers by Linda Ness that the square norm of the moment map is actually the basic function, and that's a relatively new discovery. And there are several geometries. In other words, there are two geometries, which means that if you have functions, you can get two different gradient flows, depending on which one you're thinking about. The first is the geometry of embedding the script W in the linear space. It actually consists of invertible matrices, but it sits in the space of all matrices, which is a linear space. The second is the identification of the W of X, which is the set of all W's that multiply through to X. You can also identify it with G, because when you look at the group action, it's exactly the space of matrices, it's identical to the space of matrices that multiply out to a fixed constant. So anyway, in going to the n infinity limit, we get the following. We set WP equal to, the question is, by the way, if this can be made rigorous. This is heuristic, and I don't actually see how to make it rigorous. But so if you choose as WP something that's very close to the identity. I mean, you're going to multiply these together, and you're going to want the product to be reasonable size. You're going to have to make them almost the identity. So, and then in the limit, you get, instead of the W's, you get an A, which is the function from the real line to group of matrices, n by n matrices. And we'll call that script A. And the group that's acting at every point, we just use the same group, but we not, instead of calling it little gp, we'll call it little gp over n, meaning we've actually taken the n different matrices multiplied together, and we've all stuck them in an interval and parameterized them equally. And then so when you do this, you get a lot of, and when you've done this, you get a lot of formulas for exactly the things that we had in the finite dimensional case. Multiplication of the group A by the group looks like this. It's actually, where does the derivative come from? The derivative comes from that you actually end up subtracting the different something at p and something at p minus p plus 1. Take something at p plus 1 and something at p, and you subtract them. But you parameterize that as p plus 1 over n and p over n. So which way, if you divide by 1 over n, this is approximately a derivative. So that's all that's really going on in all this, is you actually make this identification, and then you have a limit that you have a concept of a limit. And by the way, I mean, I'm not actually saying this is rigorous. I'm saying that this gives you a model, and then this gives you the model. I mean, so this all works out. I wouldn't be talking about it if it all didn't work out. But it's not a proof that if you take large N, large capital N, that it's actually going to look like this. On the other hand, you might actually think, maybe you should think about what the infinite dimensional version thing looks like when you're actually doing the numerics for the finite dimensional one. It might be wise. For example, I guess I'll say, for example, I'll say that later, but for example, the sum x, the sum of x squared, the sum of the parameters of xn is very large. I mean, because everything looks like the identity plus something very small. And so when you add it up, you get something that's of size n, capital N. And so that function is not good. It's actually not, doesn't seem like a wise one to use, and even just for large n, because you're getting into so that's where I think the infinite dimensional model is interesting. And see, so that's the formula, and then you also have the formula that x over pn is wp times the wn, and in the end you make the x go from 0, 1 to the general glmc, and then the g, and this is important. And this is also something numerically. You do have to start out with a fixed thing on the right-hand side. That is, you do have to start with x being the identity at the order of one. It's not arbitrary, because if you let the x on the end be arbitrary, you'll actually have canceled out all the extra parameters, and it's not. So carrying that argument out, you get the formula that ddx of x is ax. So actually, you're getting a representation. Well, in this construction, you're not only getting a limit, but the parameter x becomes an important part of the calculations, whereas in the finite dimensional case, the parameter x is not used so much. But so let me give you a calculation. I told you it talks about the passage to the limit. It all stems the identification of WP equal the identity plus 1 over n times a of p over n, where a is the differentiable function. So you write it all out as it is, and well, I mean this is not you've seen that I've done. You actually pull out a 1 over n, and you get the difference between x at p plus 1 over n and x at p over n, and you get a term down here. And of course, this term, the x at p plus 1 and the xp are going to be the same because you're taking a limit as that gets to 0. And so in the limit as you get there, you get the d dx with x is ax. And so as I said, this is heuristic because once you have the model, you can just work with it by yourself. But this is how you come up with the model. I suppose that's typically the way math works. And then somebody will, if it turns out to be interesting, people will spend an awful lot of time showing that the limit is rigorous. Corresponding to the list of properties for finite n, we have the symmetry group is again the maps to the unitary group. And again, don't forget to put the fact that G is 0 is the identity at the endpoints, because G is not supposed to move the endpoints, and because it doesn't move the left endpoint because that's x and you're trying to keep it fixed. It doesn't move the right endpoint, which is the identity, because you have to fix the right endpoint or you lose the extra parameter you gain. So the moment map becomes, again, you get the derivatives where you get from differences between p over n and p plus 1 over n and p over n. And you get the omega is the derivative of a plus a star minus a star, which it's the moment, and it turns out this is the moment map for the symmetry group of the U infinity group. And as I said before, the regularizing function w squared becomes infinite and not subject to passage to the limit. The function omega squared which is the square norm of the moment map. It's interesting here. What happens is this integral becomes infinite. This becomes infinite. This one actually becomes 0. That is, if you write it down and look it out, you have to multiply it by n squared before you get. So one of these goes to 0 and one of them goes to infinity. But the one that goes to 0 can be renormalized to get you an answer. So that's the natural topology. The natural topology. The analysis here is very simple. Remember that I said that this is actually the next thing you're going to discover is that why this is Yang-Mills. And the point is that Yang-Mills is good. All the analysis is simple up to dimension 4. Dimension 4 doesn't quite work. And so that's the scale invariant case. And we're at dimension 1. So the analysis is particularly simple. So the point is that A is which is it's actually a differential is in H1. That's the functions. It has one derivative in L2. G is in H2. It has two derivatives in L2. And omega is in H0. And here HK is the Hilbert space of functions. And this is And as I said, this is not natural by any way of doing it. There are two geometries I can use, which are used to compute the gradients for omega squared. See, I don't have a whole lot of a choice. One is the linear geometry. It's the linear geometry is also the one that's used in Yang-Mills. And it results in a gradient flow, which is a heat equation. I mean, we're not in the ODE situation here. Now, heat equations work pretty well. People, Emerson, Seals, and Sampson used them for they've been used, but they're a little less straightforward. The second one is derived from looking at one of the models that Govind Menon has. It comes up with the ddt of omega is equal to omega. This formula. And so if I do that, just as guess, I couldn't carry out the computation. I couldn't carry out the computation. I carried out this formula. I said, well, let's suppose that ddt of omega is equal to omega. I just write that out as a formula and write out all the formulas that happen. And it turns out that, lo and behold, this comes out with a legitimate ODE on the parameter space. So this in other words results in not an ODE on a finite dimensional space, but this results in an ODE on an infinite dimensional space. So that's one. So as I said, the reason I got into this was because I could see it looked like Yang-Mills. And so I thought I would just explain why it looked like. So actually, Yang-Mills equations, when dimensionally reduced, give a lot of standard models. They give monopoles if you dimensionally 2 by 1. They give something like Sine-Gordon equations, and when you dimension and reduce them by 2. And I've never seen a problem that dimensionally reduces them down to 1 dimension. That's exciting just to know that this happened. So yeah. In other words, what the Yang-Mills equations has to do with a connection one field, the y by plus this is a connection which I'm thinking is being on the torus, and it's on the torus, and so now I say let's suppose it doesn't depend on y. So when it doesn't depend on y, but you don't throw away the h. You keep the h. And when you have a parameter space like this, and you make you throw away the invariance of this, then you get d dx minus u h, and this is the curvature of the connection. Okay. I'm sorry. So, yeah. So, in other words, in studying this, what's used is the square norm of the curvature is the functional that's used, and in the proofs that are in the literature, the heat equation version of the gradient flow is used. So if we look at, so as I said, the curvature is now, I've written it down here, this is the curvature. The extra, here's the difference. The I here is because we've identified the dual for the algebra, not the collective game. So, so the convection with the n equal infinity model is that A is H plus U, A star is H minus U. So H dual is H and U dual is U. So, so, uh, so, so we make the computation of what our definition of omega was. And then we see that it turns out to be twice the definition of the curvature that I got this way. This was, so we get the same, omega, the moment map. Oh, and it's actually known, by the way, that's in the literature, the T about paper is that the curvature is the moment map for the action of the real gauge group. I mean, the gauge group that keeps everything fixed. It's complicated here because real in this case means unitary. Complex means the full general group. But you need to think of it that way. That's okay. So and the boundary conditions are a bit more of a problem. Because, I mean, one can rework everything for the boundary conditions given here, but it actually turned out to be quite insightful to actually reduce them. In other words, we're now on the circle. So now we're now from 0 to 1, and we double it from -1 to 1. And then we put a identification of -x with x. And the h of x is h of minus x, u of x is minus u of x, and g of minus x star, there's a -1 missing, g of -1 of x star is g of x -1. Okay. So there's a slight difference in the symmetry group, in particular. The natural choice for the U's is actually not very compatible with the choice for U's that are used in the literature here. So I don't actually know. It's just actually, which leads that when you're looking at the numerics, you want to look carefully at the numerics of how you're handling the parameter U. That's the okay. That's that. So I did get to come to my last thing. So anyway, but I said I'd done 2 things on minimization problems that were completely new to me since I gave a previous talk, and so my former student, George Rapalowitz, and I studied best Lipschitz maps between hyperbolic surfaces. This is an investigation that this was an investigation actually suggested by Thurston and his modeling of type-holder space on best Lipschitz maps. This is interesting from the 90s. The preprints were never published in there from the 90s, and no one seems to have looked at this problem before from the analysis point of view. So the Lipschitz norm is the maximum of the distance between 2 points in the image divided by the distance between the 2 points in the domain. So, and a best Lipschitz map is a U such that the best Lipschitz norm of U of L is less than or equal to the Lipschitz norm of any other map that's homotopy to it. It's not really again, this is not a problem in the calculus variations, but you can approximate it by a slightly different p harmonic one. And let p go to infinity. again, I seem to like to take things to infinity, I suppose. That's, so to do this, actually what we need is we define a tensor, which is we take the du, we take df and df, and we actually contract under these parameters and leave free the parameters in the f. So this quadratic form maps the tangent space at the function image to the tangent space of the function image. It's a symmetric product here. And note that actually what's the point of this? The trace of q to the p du is the sum of the singular values of to the power p. So instead of looking at the p harmonic would take the norm of the derivative to the pth power, whereas this takes the individual singular points and multiplies each one to the pth power. So the theorem is that you can get Best-Lipschitz map by approximating this. And I mean, it was an interesting result. It's kind of interesting. I've never had trouble publishing a paper before, but we haven't been able to get anybody to even look at that paper. It goes to a journal and it sits there for years, even with nagging. So it's interesting that. But on the other hand, people are using the result. That is, it's not like it's not interesting. It's just that they can't seem to get a referee. Okay, but now this was interesting, but in looking at the geometry and the application to tight corner space, the most interesting thing wasn't the existence of that. The interesting developed was the existence of dual measures. That is, somehow there was something hidden in the problem when the manifolds were hyperbolic. They come from those local symmetries of M and the Inertis theorem. Yeah, I mentioned Inertis theorem way back. I said there you had this integral and it was time independent. And so when I actually could find, and I could reduce, in that case, the dimension was 1. And so the divergence-free vector field corresponds to a constant as a thing. And in this case, Nerges theorem, Nerges states her theorem. If you have the symmetry of the integral, then you have, she uses divergence-free vector field. But a divergence-free vector field at a volume form are the same as a closed n-1 form. So you see, actually, 2 dimensions is very specific here because n-1 is 2. So you get a closed 1 form. So in the problems we were looking at closed 1 forms, which means we had which is getting your head around closed n-1 forms is actually much more difficult. Notice there in the presence of, oh yeah, right, I said, in this section of I said all that already. Okay. So so I want to go back to that problem that bugged me when I was a graduate student. And of course, when I was a graduate student, my thesis advisor, who was a very wise man, suggested I look up Nerges theorem. But to be honest with you, I just never understood it. I couldn't find a good reference, and I never understood it. So in any case, the suggestion now for a problem is to give M and N hyperbolic manifolds with dimension bigger than 2, and you have a harmonic. You're in the class of diffeomorphism, and so you get a harmonic map courtesy of Eels and Sampson. Now, on the other hand, now I know I learned about conservation laws from this investigation with George on Best-Lipschitz map. So So I thought, well, okay, that was the missing link. We should be able to prove the Lockdale's theorem, we just construct the harmonic map. We look at the conservation laws. We've got a set of conservation laws from the image, which is a hyperbolic manifold. And they're local, but that's all Newton's theorem needs. It doesn't say anything about, so you have a set of conservation laws from the image, and you have a set of conservation laws from the end. And, well, sorry, I skipped this. Right. Right, okay, so, yeah, I'm sorry, I got sidetracked. Okay, but now, so what are the conservation laws? I thought I would show you, the first, for harmonic maps, not for, they're more complicated for the problem we were looking at. For hyperbolic maps in dimension n, the Euler-Lagrange equations for harmonic maps are equivalent to d star du cos du is 0. This guy here sits in R, naturally in R21, which is a linear space. And so the du cos u is a closed, star of du cos du is a closed n-1 form. So that's one set of conservation laws. The conservation laws, which come from the domain, come from a tensor which is used a lot by mathematicians. I mean, anybody in the subject will recognize it. These equations are the covariant derivative of, this is now a symmetric product of one forms. And this is G is just the metric, which is a symmetric product of one forms. It sits in the same space. And so this is used, this is used for all problems that have a monotonicity theorem or something like that. And this tensor is actually how you have a tensor like this anytime you have kind of a natural, you don't have any input from the base aside from the derivatives. So it's on the other hand, this is covariant derivative because this is a product of one forms. And to take a product of one forms, you need some more data. And so that's encoded in the fact that this is. So, but on the other hand, this took us a while, but on the other hand, if you have an infinitesimal isometry or a Killing vector field, and you insert it in the integral, you get that this is a closed. Now this now becomes a closed n minus this integral here with the insertion of the infinitesimal isometry is 0. So actually, the conservation law is actually sitting in a bundle. I mean, the bundle is naturally defined by the group action. And the conservation law, the Newton's theorem, is actually in a flat bundle, which is constructed using the group action. So it seems to me that this is the way that I would prove Newton's theorem if I'd been smarter when I was a graduate student and had understood Newton's theorem. But so I thought, oh, well, this is a no-brainer. I'll go back and do it now. And I can't do it. I don't know. You know, it's I don't know. And I even cheat. Namely, I looked at all the other proofs too, you know. But anyway, so and I figure if I tell enough people about it, I don't care if I solve it, but I'd really like to see that it's really a question of understanding some geometry somewhere properly. Anyway, so that brings me back to and I don't think in another 7 years I'll could talk again though. Thank you.
Thank you very much, Karin, for a very fascinating talk. We have time for questions or remarks from the audience.
So of course, after Colette, the harmonic map proof of rigidity, superrigidity,
Yeah,
cover, but only everything but hyperbolic space. I mean,
Yeah.
suited complex hyperbolic space this way.
Oh, complex hyperbolic spaces work better.
Suit.
Yeah, but for the complex hyperbolic spaces work.
Yeah.
I mean, that's the harmonic map is
Yeah,
actually,
right.
I think it's actually, complex. I mean,
Right,
it's a
right.
complex map. But no, of course I've looked at that, but I mean, that was discovered almost right away. You know, it isn't something that.
Any other questions? If not, let's thank Karin once more.